Okay, hi. Let me begin with the quick story. Imagine the situation when you are standing in a shop queue and the first person in the line suddenly reminds that he forgot his wallet. And they can't pay for his goods, so he needs to go to the car to grab the wallet and then back to the shop to make the payment. Meanwhile, even if the shop assistant can serve the next person in the line, she also suddenly realized that she had open transaction, which that prevents her from moving to the next customer. Can you imagine that similar issue with the open transaction can occur into the Python? Imagine I tell you, no matter what this function does for this moment, but when this application is under heavy usage, this specific part of the code can handle around 30 requests per second using SQLAlchemy. But guess what? If we swap out SQLAlchemy with databases, it can handle 170 requests per second. And here is really good news. By making few changes and knowing a little bit about SQLAlchemy, we can improve the SQLAlchemy to handle 170 requests per second. Sound interesting? So let's deep dive into asynchronous SQLAlchemy, transactions, and connections. Before we delve into the details, let me a brief about myself. I have been working with Python for 7 years now. 6. Yeah. But that's not all. I'm also a mentor at Lithuania Starter. This is our initiative when we learn Python from scratch in the high school. On the top of that, I organize local IT meetup called MeetTech in Poland. Okay, so let's jump into the code. Let's start with the first example when we call it implicit transaction example. First, we'll create an ASIC engine with the pool size of 5, followed by a simple function to retrieve the session, which will be used as a dependency injection. It's important to note that we are using SQLAlchemy, which in context of Fast API, so we initialize the Fast API app. For the sake of clarity, we'll omit this code from subsequent examples since it's remained the same. Finally, we have async function that handle HTTP GET method. This function retrieve and return the node based on node ID. The getNode function used inject the database object, which is equal to SQLAlchemy session object. Okay, so let's dig a bit deeper into the details. On the left, we have our code, and on the right, we have logs generated by our application. These logs are essential for us to understand what's happening in terms of how SQLAlchemy manages session through the dependency injection. Now we will execute this function and analyze it line by line to see what logs it will generate. Okay, so as you can see, we are on the third line, and our function already have access to the database object. We can notice that no logs is produced at this time, which means no connection is acquired at this moment, right? So moving forward, we are currently on the 5th line, and we can observe that we receive some logs. The connection is actually acquired. Once we acquire the connection, the transaction begins implicitly, and after that we can see our select statement. Let's move forward. After exiting the function, we notice the next set of logs appearing. From these logs, we can see that we return response first. Following that, SQLAlchemy performs a rollback, and then connection is released. Let's pause for the moment and pay attention to a few important details here. Firstly, SQLAlchemy automatically starts the transaction, which means that the connection and transaction are closely linked. Secondly, we observe that even for simple select statements, SQLAlchemy proceeds with a rollback to close the transaction. Here we have a simplified request lifecycle in FastAPI, focusing only on the interesting steps because this is the not presentation about FastAPI itself. So, in the third step, we have dependency injection, which creates a SQLAlchemy session. Moving on the fourth step, we execute the request, acquiring the connection and creating the transaction. Moving on. On the ninth step, we return the response. Finally, in the last 10th step, the transaction is closed, connection is released, and the session is closed. This is accomplished by the ASIC exit stack, which is middleware provided by FastAPI. An important observation here is that we are wasting resource, which is connection to the database. We actually only need the connection during the fourth step, which is the request execution, right? However, we keep the connection acquired through the entire request lifecycle until the last step. Right, so we execute our request just right here, but we keep the connection total to the end of the request lifecycle. Okay, so what we can do with that? Let's see possible solution. Here is the code from the previous example. Let's introduce some modification. One noticeable change is that we've wrapped our code with database begin statement. Once again, we will go through the code line by line and examine the logs that will appear on the right side. Okay, now we are in the context manager. We have access to the database object. We also started session with the database begin, but still no logs appear. So that means there is the connection is not acquired yet. Okay, as we observed previously, the first set of logs appear on the 6th line, which corresponds to the database execute operation. So far, nothing changed. Upon exiting the context manager, the next set of logs becomes visible. We noticed a commit happening, followed by release the connection. Here we can observe a change compared to the previous example. Instead of rollback, we have commit statement. Now, when we exit the function, the logs show that we return the response. In this example, we release the connection first and then return the response. This approach appears to be an improvement, right? So now let's compare the logs from these two approaches. As mentioned earlier, we have made a significant improvement here. We can see on the right-hand side, we release the connection first, followed by returning the response. Furthermore, it's worth noting that in both examples, we still observe the occurrence of rollback or commit. This behavior is inherent to SQLAlchemy management of transactions and connections. To gain a deeper understanding of how the solution works and where it fits in our request life cycle request of Fast API, let's merge our two examples into one. In our first example, which we are already familiar with, we acquired the connection on the fourth step and released the connection on the 10th step. Now let's examine how it looks in the case of proposed solution. We can clearly see a notable improvement in this case as we acquired and released the connection on within the same fourth step. This aligns with our desired objective because we now have connection only when it's needed, especially during the request execution. As soon as no longer we require the connection, we promptly release it. So, to summarize what we learned so far, we now understand the close relationship between transactions and connections. SQLAlchemy handles certain operation implicitly, which is why it's important to be aware what is happening behind the scenes. We also discovered that even for simple select statement, the transaction is initialized implicitly. Furthermore, to release the connection, we need to close the transaction, which explains why we may observe an implicit rollback or commit, even if we do not explicit execute. Let's dive into the more practical example using the knowledge that we gained earlier. We'll break down this example into smaller pieces. So, in this example, we have set pool size to 5, meaning we have only 5 available connections to the database. This scenario involves handling HTTP post request. Here's breakdown of what's happening. We validate the node ID. We then execute a select statement to retrieve external ID from our database. This ID is used to call an external API for the node synchronization. It's important to note that this external API call takes around 5 seconds to complete. This assumption is made for test purpose. Once we retrieve the response from the external API, we update our node with the data provided by external service. Finally, we return the response. So, at first glance, this function might seem like typical, well-implemented one. All possible I/O blocking functions are awaited, and no apparent bottlenecks are observed. Right? Everything looks correct on this code. So again, this looks like normal async function, right? So let's test it. Now let's analyze the benchmarks to assess the situation. We'll begin with 5 concurrent requests. As we can observe, each request took approximately 5 seconds, which aligns with our expectations since the call to the external API. We assume that it will take 5 seconds, right? So far, everything appeared to be functionally correct, right? Now, let's proceed with running the same benchmark, but this time for 10 concurrent requests. Here's what we find. The first 5 requests take 5 seconds each. However, the subsequent 5 requests take approximately 10 seconds each. This doubling of the response time for this second group of requests indicates the presence of bottleneck and suggests that something is wrong. Let's analyze the situation by break it down visually. In this animation, we'll start from the left side. We have multiple requests represented by colors matching the colors in our benchmarks. These requests are divided into 2 groups, blue and purple. In the middle, we have a connection pool that consists of 5 available connections. On the right-hand side, we can see either purple or blue arrow pointing to the specific line of the code as the request is being handled. The color of a given arrow is associated with a corresponding request to the left. Okay, let's start. We'll start of the 9 line of the code where the database execute operation occurs. At this point, we'll notice that the blue group of the request occupies all available connections. These connections are indicated as green, indicating that these requests are performing database operation. After that, the blue group makes 5 concurrent API calls to external service. Once the 5 seconds have passed, the blue group receives the response from the external API and proceed with the database update operation. It's important to note that during this time, the purple group is still waiting on the 9 line as the connections are unavailable. Once again, the blue group retrieved the response from the external API and the connection turned green to perform the update operation. After the commit, the connections are released back to the connection pool. The blue group returns the response and complete its task after 5 seconds. The purple group can now acquire this connection to retrieve the external ID needed for making a call to external API. The connections turn green during the database operation. Now the purple group made the call to the external API, which takes 5 seconds. After the 5-second interval, when the response from the external API is received, we can see that the purple group proceeds with the update operation as indicated by green connection. After the commit, the connections are released back to the connection pool, and purple group is ready to return the responses. From this analysis, we can identify the bottleneck. We keep the connection even if we don't need them. In this example, we may call to the external API, which takes around 5 seconds. During this time, the blue group occupies all available connections. This prevents purple group from getting connections from themselves. Initially, it might not be obvious that the number of available connections could be a bottleneck in the seemingly normal asynchronous function. Now we know that the bottleneck is causing our connections to be kept for too long, since we unnecessarily waiting for the external API call to finish. This had a great impact on the performance of our web application, as we don't release the connection as soon as we could. Simply increasing the number of the connections would be a temporary solution and wouldn't address a root cause. To tackle this problem, we need to modify our code that will better manage the connections. As you can see, we have wrapped every database execute call with database begin. This will ensure that the connection is released after the execute is called. Now let's revisit our visualization and observe the changes that we have made. So this is our visualization from the previous slides, but with the modified code that we did in last slide. So let's see what happened here. Once again, we pause at the 11th line where the database executes take place. The blue groups acquired all available connections and proceed with respective database operation. As the connection turned green, we know that execute operation is complete. Now, as the blue group exit the context manager, the connections are really released. The purple group take advantage of this and acquire the connection to perform their select operation. Meanwhile, the blue group makes an external call to the API. It's important to note that not much time elapsed before both groups make call to external API. After the 5-second mark, we can see that both groups halt at the database execute operation once again. The blue group grab the connection to carry out their database operations. Yeah, after the commit and exiting the context manager, the blue group, the connections are released to the connection pool, and blue group is ready to return the response. Now the purple group can proceed with their database operations since the connections are available once again. As the purple group concludes their database operation and commit it, the connections are released, and purple group could return the response. By implementing these changes, we have greatly improved the performance and eliminated the bottleneck caused by the exhausted connections. Let's see how our solution matches to our benchmarks that we did previously. Yeah, as we can notice, our solution gives us expected performance, right? Now both groups need around 5 seconds to complete their task. Okay, so what do programmers love the most? Diagrams. That's right. I have two diagrams here available that provide a more detailed visual representation of where the resource was being wasted. Unfortunately, due to time constraint, we won't be able to delve them further, but you can scan QR code if you want to check those diagrams later. Okay, so as a bonus, let's take a look at how other library named encode databases manage the connections. Oh. Okay, this is our code that we already know. This is our bad example with performance issue, right? Let's modify it using databases. As you can notice, only one thing changed. Here is how we initialize the database engine, because the databases understand SQLAlchemy dialect. To give you more context, this is how the whole code looks like with the connection to the database. So now I would like to show you more real benchmarks. This is the specification of the benchmark. We will run benchmarks with 1,000 concurrent user of our application, and our application will have 10 available connection, and we will run it on one worker. So this is our first example with the performance issue related to bad management of the connection. As we can see from the bar chart, we are able to handle around 30 requests per second. This is benchmark for the code with our improvement, with the connection management. With the improvement of the connection management. As we can see, we have significant improvement here. Now we can handle around 170 requests per second. And let's shift our attention to our underdog databases. In this example, we have modified our code to use databases for connecting to the database. As you can see, this code is fast, similar to the previous one. It also can handle around 170 requests per second. The key difference is that databases released the connection after every execute operation. Unlike SQLAlchemy, it does not provide implicit transaction, which contributes to the higher performance as we observe. So, for the summary, for those who are familiar with Zen of Python, explicit is better than implicit. We should release the connection as fast as soon as possible, And one thing also to notice is that connections are passed as reference. What this means? Maybe from this example, we not creating every time the connection to the database, right? We only passing it as a reference, okay? And that's all. Thank you.
So it's time for questions.
Yeah, it's time for questions.
already being on online, do you have any issues with safety with these things?
With safety?
Threat safety.
Threat safety. No, we didn't have. Our main issue was the performance issue, because how SQLAlchemy managed those transactions, and because of implicit transactions, right? Okay.
Yeah, I have a question. It's kind of topic. Do you know the cases when you shouldn't use SQLAlchemy or any kind of other ORM, so stick with a plain SQL statements or SQL? Are there any cases when that's more beneficial? Because I have a team, we're building an app, we have the exact same stack, and we have like a couple of abstraction layers, and it makes SQLAlchemy kind of obsolete in some cases. So we're considering if we should just start a bit from scratch and just use raw SQL.
Each ORM has own issues, right? The SQLAlchemy, it seems like, is most major one. It's really hard to say. I'm programmer, so I will say it depends, right? But it also depends on your team. If your team is really excellent in SQLAlchemy, yeah, you should go with the SQLAlchemy, because learning the new things, right? If you have expertise in SQLAlchemy, could be more time wasting with learning new things and discovering new issues to them.
And there's one more question on our channel. So someone asked to share the slides. Is it possible to share the slides?
Yeah, sure. Those slides are public. I will send.
You can just drop a link in the.
Yeah, I will drop the link just after this talk.
So one more round of applause.